Assalamualaikum warahmatullahi wabarakatuh. So today we are going to discuss about IR spectroscopy and also Nmr spectroscopy. IR spectroscopy is a study of interaction between infrared radiation and matter by measuring their absorption, emission and also reflection. It can be used to determine the functional groups present in molecules. There are two conditions for absorption to occur. The first one is that there must be a change in dipole moment of the molecules due to the molecular vibration. It will allow the interaction with the electrical component of IR radiation wave. The dipole moment change will cause symmetric vibration, antisymmetric vibration, and also deformation. Different chemical bonds will absorb different IR frequency. The second one is that the frequency of the radiation must match with the natural frequency of the vibration. The absorption will occur, hence will increase the amplitude of vibration. Constructive interference. The basic mechanism of IR spectrophotometer. First, we need infrared light from a fitting source. Light is then directed at the samples. Some lights are going to be reflected, but less of it are going to be absorbed by the sample. The transmitted light will carry the molecular information of the sample and can be collected by the detector. The transmission spectrum can be obtained from sample and reference spectrum. Next is Nmr spectroscopy. It is an analysis that concerns of magnetic property of certain nuclei. In this case is hydrogen. It can be used to elucidate the number and types of hydrogen in compound by identifying their carbon-oxygen framework. Principle of Nmr spectroscopy. The hydrogen in the nuclei behave as a tiny magnet. There are two energy states. The lower one with the nucleus with the same direction as B0, which is external force, and the upper one with higher energy and less stable, with the opposite direction of B0, a radiation which equal to the energy difference of the two states will be absorbed. So the nucleus will spin flip into another orientation, into a higher energy state. The higher the magnetic field, the higher the energy difference between the two states, and also the higher the frequency of the absorption. Since hydrogen can absorb slightly different frequency, their resonance can be observed by NMR.
Next, we move on to the next section, which is interpreting infrared spectra of compound C. To interpret the IR spectra, first we need to know the wave number of each type of bond. The frequency of oscillation of any chemical bond is related to a quantity known as wave number. The greater the frequency of oscillation of our chemical bond, the greater the wave number. So based on this table, we're going to match the wave number given in IR spectra of compound C. So we can find what is actually compound C. Every time we interpret IR spectra, first we need to draw a line at 1500 and 3000. The region below 1500 we call as fingerprint region. And normally we ignore this region because it is much more difficult to find the individual bonds in this region than the region with higher wave number. Notice that there is one signal that fell on 1500 wave number, and we already asked our lecturers about this situation, and we actually can consider this line included in the fingerprint area. If we start at 1500 and move to the left, the first thing we encounter is a very sharp signal, like a needle, and the wave number of this signal is around 1600. And if we look at the table of wave number, this wave number is actually belongs to a benzene ring. The next obvious signal that we encounter in this spectra is a quite sharp signal that lies above 3000, and there are three possible bonds that can be found here, which are NH bond, OH bond, and aromatic CH bond. Note that the intensity of this type of bond is different. The intensity of NH and OH bonds are broader compared to CH bond. The intensity of CH, aromatic CH bond is more sharp than NH and OH bonds. So this medium sharp signal tell us that it represents the aromatic CH bond, where there is double bond attached to the carbon of the CH bond. Since we got benzene ring and aromatic CH bond in this spectra, it can be concluded that this functional group or type of bond match the structure of naphthalene, where there are two benzene ring and aromatic CH bond in its structure. So compound C is actually naphthalene.
Assalamualaikum. Now we move on to study the Nmr spectroscopy of compound F and to confirm whether the spectrum belongs to paracetamol. There are a few information that we can use to relate the characteristic of the peaks with the structure of the compound. They are chemical shift, integration, and splitting. Chemical shift tells us the chemical environment of the proton. It depends on the presence and distance of the proton with the electronegative atoms. It is a result of the shielding of this proton. In other words, the closer the hydrogen to the electronegative atom, the more downfield the peak is. Next is the integration or intensity, which tells us the relative amount of protons with equivalent chemical environment. The higher the number of protons in a group, the greater its intensity. Third one is splitting. Splitting of peaks suggests the presence and quantity of neighboring protons present. It is denoted by n plus 1, where n is the number of neighboring protons. The peaks can either be singlet, doublet, or triplet. This is a given Nmr spectrum, and we can observe that there are 5 peaks, suggesting that there are 5 groups of protons in the molecule. We can vaguely predict the functional group and their connectivity based on these values. However, now we want to confirm whether this spectrum belongs to paracetamol or not. So we need to look at the structure of paracetamol. Take note that there are several functional groups present. First step is to write all the protons of the paracetamol to make it easy for us to group them. Protons that have identical chemical environment, no matter how the stereochemistry is, will be grouped together. Hence, the hydrogen of methyl group will be group A. Group B is a single proton bonded to nitrogen. Group C and D are the protons of benzene, and they differ by the oxygen and nitrogen atoms that are closer to them. Last group is the hydrogen of hydroxyl group, and we will take it as group E. To assign the groups to their peaks, we need to examine the groups based on their structure. Group A consists of 3 chemically equivalent protons, so we can say that the peak will have a relative intensity of 3. There are no neighboring protons, hence it is a singlet. Group B and E both have only 1 proton each and no neighboring proton, so they are also a singlet. Group C and D have 2 protons in a group and 1 neighboring protons each, so we expect the peaks to be doublet. Now we will try to assign the groups to their peaks. Group A has the most amount of proton. Its peak is the highest in the spectrum. Group C and D will have the same peak height, and their difference is that group C is closer to nitrogen while group D is closer to oxygen atom. Take note that since oxygen is more electronegative atom than nitrogen, the position of group D is more downfield than C. Lastly, the hydrogen of hydroxyl group or group E is located further than group B in the spectrum, also for the same reason being that oxygen is more electronegative than nitrogen. Therefore, we are able to confirm compound F as paracetamol by assigning its proton groups to the peaks of the spectrum.
The next part is the comparison of IR and NMR spectroscopy. Both IR and NMR spectroscopy are the form of absorption spectroscopy, which use an electromagnetic spectrum to be absorbed by the substance. IR spectroscopy identifies chemical substances or functional groups in the molecules, while NMR spectroscopy determines the content and purity of a sample as well as its molecular structure. Usually we use NMR spectroscopy to study the types of hydrogen present. Alright, so IR spectroscopy uses infrared radiation, which can be divided into three regions: near infrared, middle infrared, and also far infrared, with wavelength 0.8 to 1000 micrometer and the frequency 430 terahertz until 300 gigahertz. NMR spectroscopy uses radio wave radiation with radio frequency 4 to 900 MHz and the wavelength region 0.6 until 10 meter. The graph of IR spectroscopy represents percentage transmittance at y-axis and the wavelength of radiation in reciprocal centimeter at x-axis, while the graph of NMR spectroscopy represents the absorption of energy at y-axis and the chemical shift at x-axis. For the applications, IR spectroscopy usually suitable for identification of drugs metabolites, for the study of interaction of drugs or excipients in formulations, and also the patterns of antibiotics. Meanwhile, for NMR spectroscopy, it is suitable for determination of 3D structure of proteins, and for other applications that apply the same principle is magnetic resonance imaging, MRI, and also for oil and natural gas exploration. There are some advantages and also disadvantages of IR and NMR spectroscopy. IR spectroscopy is suitable for a wide variety of sample types, such as tablets and capsules. It is fast and largely qualitative analysis and also suitable for solid-state analysis. Thus, it is selective for APIs and excipients. But to use IR spectroscopy, we need to bear that it cannot determine the molecular weight of the compound and also provide information about the relative position of functional groups. For similar infrared spectra, it tends to misidentify the fingerprint region, and it requires pure compounds. Meanwhile, for NMR spectroscopy, it can provide the determination of the structure accurately. It also can be used to study the structure of proteins in 3D structure, and it can examine the molecular parameters such as chemical shift. But to use NMR spectroscopy, it requires high concentration of soluble protein. Next, the experimental implementation is also quite expensive. NMR spectroscopy is not capable for higher molecular masses of proteins, which is limited to 64 kilodalton protein complex. So which one is better? Actually, it is depend on our study. For example, if we want to identify the functional groups of the molecules, it is better if we use the IR spectroscopy. But if we want to determine the molecular structure of proteins, for example, it is better if we use the NMR spectroscopy. We need to clarify what is our objective in our study and what we want to observe. So, we can choose the preferable technique for our study.